All right, so this is going to be a little bit of an experiment. What I'll be doing in this video, or at least attempt to do, is to basically do mathematics, and I will be investigating a vague problem or some set of ideas that I had. And sort of as I do that, I want to share my thought process, both with you, but also for myself later to check what my thought process is. It's sort of taken from a video, or a bunch of videos actually, by a guy called Tim Gowers, who had some specific problems that he was given and or found and wanted to solve them, and do that while recording his thought process. So basically, I'm doing the same thing as he did for similar reasons. I also wanted to go a little bit beyond that by looking at problems that, well, are not really problems in themselves, in the sense that the problem is fixed, but more of like, okay, here's some mathematical behavior that we see, let's investigate that and let's see what we can find. So it's a little bit more freeform. So hopefully it gives you some idea of at least how I do mathematics, or at least will try to do mathematics. I'm not sure where I'll end up. So let's see. And this is also for myself to sort of see my own thought process. And I thought it would be a good excuse to sort of really focus on doing mathematics because I'm quite easily distracted, and having a camera pointed at you is, of course, a very good way to focus oneself. That being said, let me get started. So what do I want to look at? It's inspired by a few things. Let me see. So there's this following fact that if I have a polynomial of, let's say, degree d, then if I specify d points, or maybe it's even d plus 1, I'm not actually sure now, then you can figure out the polynomial itself. So you're given a polynomial, let's say p, capital Px, and if you know values px sub I, or I believe this should be d, it might be d plus 1. But if you know these, then you can find all values. And I think this is the Lagrange interpolation theorem, and has a lot of applications. Sort of, I guess, one straightforward idea is that if you have some function and you believe that it's a polynomial, then you can just sample it at sufficient points and then extract the coefficients from there. So I might actually look at this, try to see how one can derive how to do this actually. I wanted to do something a little bit more simple, a little bit different at least. But this is sort of a classic fact. And actually, maybe as a first check, let's see whether we need d or d plus 1. And I guess sort of the standard one test case that we can try is just evaluating some polynomial, let's say px equals to, well, let's say a plus bx. Or maybe you could have just chosen a constant term. In fact, yeah, let's choose a constant term. If we have just a constant polynomial, then if we evaluate it at one point, then we know it exactly. And this is a degree 0 polynomial, so that means indeed that we need a plus 1 here in general. And one can also see this if I add a linear term here, then I just get some line, and I need to have at least 2 points to specify that line. Okay, so this is already an instance of this thought process, right? Sort of double checking statements. And again, I go into this very unprepared, and I'm just making things up and trying to figure things out as I go along. Okay, great. So this is the Lagrange interpolation theorem, if I remember correctly. Now, I saw somewhere a post where people did the following. If I give you a polynomial p of x, then I can define the following map on it. Just going to move the x up 1. Right, so I'll go from x to x plus 1. And apparently this has some nice properties. So let's investigate that. Well, of course, if I write my polynomial px like this, I have some coefficients. Let's call them ai, x I to the power I goes from 0 to d. Well, then let's write down what p x plus 1 is. So we're just going to plug in and see what happens. That should be a 1, of course, to the power I. All right. Now, every time when we see an expression like this, one of the first thoughts you should have is the binomial theorem. And what does the binomial theorem say? Well, in general, if I have two terms like this, raised to the power n, then I get something like this. Let me see if I'm getting this correctly. That should be like this, times a binomial term. I also hope that my handwriting is clear enough. I hope that as I am explaining what I'm doing, that clarifies some of the notation if it's unclear. Okay, so this is what the binomial theorem tells us. So let's plug that in here, this expression. Let's move this down a little bit. So we find that this expression is equal to I 0, d. Okay, it's a little bit annoying that I'm using I here, and I'm also using I here, so I'll need to use a different index. I'll probably use j. Let me change this to j, actually, here. All right, and we plug this in. And this is quite nice, right? Because we just have a 1 here. So let's see. I want to have the let's see, 0 to j, and then I have x to the j here. Okay, let me erase this. Okay, let's see, what can we say about this? So I would like to express this again as some other polynomial. But now I have some coefficients. Oh, I'm mixing up entries. Or indices. That's a little bit annoying. But let's see. Yes, I want to write this in this fashion. No, just a mistake here. That should be an I in the exponent, not a J. So it's very easy to make mistakes like this, especially unprepared. So I would like to rewrite it in this form, right? So let's equate those terms. Let's see. Okay, so if I have a term aj, this will be mapped now to some bj, such that actually, okay, so it seems like well, this is a little bit annoying to do because I need to collect all these terms together. Okay, so what I'm going to do is the following. I want to I'm going to see what happens if I sort of move this sum to the front. Because it's a little bit annoying that I have these different x terms here with different powers. And I want to collect all the like powers together, because if I have a term like x to the j, then all the terms in front of that, that's exactly the coefficient b sub j that I'm looking for. So maybe that's one way of doing that. Okay, so okay, I'm going to be a little bit, okay, we can just move it like this. That doesn't really help us too much, I believe. Yeah, that doesn't help us a lot. That is annoying. But let's see, maybe we can still make sense out of this. Okay, I don't directly see a nice way. Okay. One thing that is annoying here is that this sum here goes up to j, and the index j is controlled by this term here, by that's sigma, that summation term. So let's sort of reverse that. If I fix some j, right? So I'm fixing the entry of x to the j. Let's write it out. X to the j. Okay, which terms can appear? Well, those are all the terms. Let's see. These are all the terms that can appear. Oh, this is getting a little bit annoying. Okay, in case you get stuck, it's always good to just run through an example and just see what happens. So let's take, okay, let's try to keep it general. All right, so this is a general quadratic polynomial. Let's plug in, let's convert x to x plus 1. So that maps to a plus b x plus 1. I'll just be explicit and write everything out. Then given by a plus bx. Okay, let's group those terms together. A plus 1. Sorry, a plus b plus b x. Let me write x here because I suspect we'll get another term here. Okay, let's expand this out. So this is just c x squared plus 2x plus 2x plus 1. We see, yes, that should be correct. Okay, so we got a plus 2 here. Okay, that's interesting. A 2, I didn't sort of expect that. And we get another c term here. Okay. So let's clean this up. Of course, this is a little bit of a mess as we're writing this out. This will become a plus b plus c. That's sort of nice. That's not a constant term. What did we get here? So that was b plus 2c. Okay, that's interesting. We get a 2c. And here we just get a cx squared. Did I do that correctly? Yes, that seems like it makes sense. So that is sort of the behavior that we saw here, right? We saw that the j term here only went up to, or sorry, the I summation index only goes up to j, which is controlled by the first summation index. And that's sort of what we're seeing here, I guess, like all these higher terms, like the b and the c, they also end up here. Here we end up with a c term, but also with this term 2 in front. And this remains, right, we just got a c there. All right. Okay, let's try to understand where this 2 comes from. Let's quickly see. Is this correct what I wrote down? Oh, yes. Okay. Oh, wow. What a silly, silly mistake. Okay. Right. So that's a good example as well. It's very easy to make mistakes. I wrote down here an n in the binomial coefficient. Now, I guess that's partially force of habit, right? When we think of the binomial theorem or binomial coefficients, it's very tempting or very easy to just write down an n. But of course, we have here an I in the exponent. So let's take a step back. Let's make sure we got this correct. I'm gonna erase this. Okay, and this just goes to show, right? It's very easy to make mistakes, and one has to balance out these calculations, doing them, and making sure you're doing it precise, but at the same time not wasting too much time. And clearly, I was on the wrong side of things there. Okay, so let's write this out specifically. Let me make a bit more space to make this hopefully a bit more clear. This is getting a little bit cramped, I'm afraid. Ah, yes, okay, so I'm gonna draw a little cloud here and write that, okay, x plus 1 to the I is, and again, we all need to be careful with the summation indices. Sum now goes to I, and let's do n. That doesn't make sense. And then we get here x to the j, binomial coefficient of I, choose j. Okay, that looks ugly. Looks weird to me to have a binomial coefficient like that, but that's just the way it is. All right, so let's plug that in. And actually, let me move that summation index a little bit to the front. Let's see. I'm not sure if that will really matter, but why not? Okay. I x to the j, choose j. All right. Now let's see if this makes more sense. One thing that would be nice is, I have this I here. That's kind of annoying. But what I do know is that if j is larger than I, then this binomial coefficient will be 0. So actually what I can do is I can just change this top index to d, which is nice because now this summation index does not depend, doesn't depend on this sum here. So let me be a little bit careless, and I think this should be all right. I can just change the summation indices, and that should make my life quite a lot simpler, I believe. Okay, let's create some more space because this is getting messy. I should be clear, normally when I write notes in my notebook, this is way more messy than what I'm presenting it now. So this is a good excuse to work maybe a little bit more organized. All right, let's change the summation indices here. It's one of the benefits of working with an iPad. You can move indices and summation indices around quite easily. All right. All right, does that simplify things? Well, what I want to do is I want to interpret this as yes, I want to interpret this as this, right? All right. So is that then just this part? Let's see. Okay, I can move this really out front, out some. And that is nice. Again, using my iPad skills. Because now I can just imagine brackets here. And that tells me then, if I'm not mistaken, that bj is given by ai j's coefficient. Let's see, does that make sense? So it's kind of weird, right? Because oh wait, no, this makes sense, I guess. Okay, let's do some example calculations. Oh, it's unfortunate, right? I want to compare this with the initial polynomial that I started off with, but I used my coefficients here were a, b, and c. So that's a little bit annoying. See, this is why I have to be careful with notation, especially when sharing with other people. All right. So let me just rewrite that. Let's say we had our initial polynomial in this form. Then we saw this got mapped to a0 plus a1 plus a2, right? These were those a plus b plus c that we had here before, but we're now changing notation. Plus a1 plus 2a2 times x plus m just plus a2x, right? That last term remained invariant. Okay, if this doesn't work, if I made a mistake, then I'll probably move on to something else for the sake of time as well, and try to investigate something else. So let's see. Does this match up? Okay, well, let's choose b0. So b0, I just plug this in. So from I0 to D, okay. And I have here now 0 in the bottom of this coefficient. Well, this term here is just always 1, right? The binomial coefficient tells you how many ways you can choose, in this case, I elements out of j elements. And since j is 0 here, there's just one way of doing that. So this just gives me the sum of of my original polynomial coefficients. So indeed, that gives me this term here. So that's reassuring. Okay, let's plug in this term here, be 1. So then we just get a 1 here. And that is also good because when we plug that in, then we get I choose 1, but that's just equal to 1. Sorry, that's equal to I, because we're choosing one object out of I elements, so we can do it in I ways. And so that tells us that we should get 0 times a0 plus 1 times a1 plus 2 times a2. That's exactly what we see here. Okay, so that is reassuring. And let's do a final double check just to see what happens. Put in now a 2 here and put in a 2 here. And now the interesting thing is that when I is equal to 0 or 1, then this term will be 0, right? Because And that's one of the properties of the binomial coefficient. Phrased another way, there's 0 ways of choosing 2 elements out of a, let's say, a 1 element set, or 0 element set for the matter. But we do get that's equal to 1 when I is equal to 2. So that recovers this. Okay, so that's good. That took us some time, but this seems to be the expression. All right. Yes. Okay, great. What have we done now? Maybe to sort of recap, we found a way to express the coefficients of the polynomial px plus 1 in terms of the coefficients of px. Okay, so again, this is just something randomly that I came across online and want to double check, see what happens. It wasn't a particularly hard calculation, but it was easy to make mistakes with notation. So what can we do now? Well, let's see. So I know that people have looked at the following. I think they call this the forward difference operator of a polynomial p, which is given by px plus 1, which we have just found, or found a way to express it in terms of px, and then we subtract px. And this just tells you, okay, if I start off with some polynomial and I calculate the value at point x, how much does it increase when I move x, as I take one step forward? So that's what the forward difference tells us. And you can really just interpret this as a sort of a discrete derivative. In particular, when I think of a derivative, I think of something like this. I move a little bit h away, and then I divide by h, and I should take the limit. But now let's just set h equal to 1, and then we recover back this original term that we had here. Okay, so now the nice thing is that this is a polynomial, and this is a polynomial. So this forward difference operator applied to our polynomial will be, again, a polynomial. So let's express that. Okay. Well, one thing that we can do is this will have some coefficients, right? This will be some polynomial ci x to the I, where ci is given by bi minus ai. So ai are the coefficients of our original polynomial. Bi are the coefficients of the polynomial where we add plus 1 to x, which we've calculated, right? That's exactly what we did here. So let's do that. This doesn't seem too nice. So maybe I'm missing something here. Yeah, okay, if I just plug that in, I get, let me make sure I have the indices correct, because that's easy to mess up, as we've seen. AI ij minus AI. And okay, again, I used unfortunate indices here. Oh, okay. This is bj. Let me switch to bj. bj, 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 bj. Okay. Now, frankly, this doesn't really look that much simpler to me. So I think I'm missing something here. It might have to do with the fact that repeating this forward difference operator is the thing you want to do. I'm not sure. let me sort of stop with this calculation for now, and sort of let me tie this back to the Lagrange interpolation theorem for a bit. So we know from the Lagrange interpolation theorem that if we know a polynomial of degree d at d plus 1 points, then we know we can reconstruct the values of the polynomial. I might try to see if I can figure out how to do that later. And the idea is that if I apply my forward difference d times, sorry, let me rephrase that. If I have p0, then I know my constant term, right? Because that's the only term that survives. So this will be a0. If I now know p1, this will be a0 plus, plus, I'm blanking there for a sec, plus oh, sorry, this will just be, okay, this will just be the sum, of course, of the AIs. And somehow the idea is that if we keep repeating this forward difference operator d times, we get here other terms, and they will uniquely specify the polynomial. So that related somehow to the Lagrange interpolation theorem. Okay, I'm not too sure. Let's put that on the back burner for now. This idea of knowing, okay, we know I have the Lagrange interpolation theorem, then you apply this forward difference operator, or sorry, just a forward operator. That means you just take px and move it to px plus 1. And by doing this sufficient number of times, you get values at very nice places, right? You get it at x, x plus 1, x plus 2, etc. And from there, reconstructing the polynomial sounded like, okay, we can do that maybe also for other nice values of x. Right, so let me sort of draw that. If I think of the real line, and let me imagine I start off at 0 here. I calculate my value now at px plus 1 here. Then I calculate it here at px plus 2, px plus 3, etc., etc. If I know those values, I can reconstruct my polynomial. What I now want to do is do the same thing, but instead of translating, as I'm doing here, I want to do rotation, which is a close analog of translation. Okay, so when we think of translation, the first thing that we should think about is really complex numbers. And so what I want to do, or I guess sort of one of the ideas that initially inspired this, I want to plug in roots of unity in my polynomial. So maybe to be clear, root of unity is, let's use the term omega. As a term like this, I have e to the power 2 pi I divided by n, and let's put a k here. Let's see, let's put here an let's put here k n, because these are the two parameters that sort of parameterize my root of unity. I need to be careful remainder with this I here. This I is here a complex number, of course, and not an index. And the idea is that, okay, if I know if I have a degree d polynomial and I know it at d plus 1 roots of unity, then I know the polynomial exactly. That just follows from the Lagrange interpolation theorem. And so that's something I wanted to investigate. Now, one nice thing that I figured out, which is not too hard to see, but I had never seen it written down anywhere before, is the following. If I have a polynomial, p of x, which is some of monomials like this, then I can interpret these AIs as a list, as a sequence of numbers, all the way up to d, and this specifies the polynomial. if I plug in roots of unity into my polynomial, what I'm really doing is I am evaluating a Fourier series. Let me maybe be a bit more explicit. If I plug in here some root of unity, right, we see we get this behavior. Oh, okay, I said I need to be careful with indices. Let's change this I, let's change this into, let's do M, I guess. Indices are the worst. There's not enough letters in the alphabet. So I got, let's see, N, there's too many, okay, actually, yes, let's just use this. Just gonna use this notation. And you will recognize this as a Fourier transform. Maybe more explicitly, this gives us a single value when we plug in this root of unity. And if I now look at this sequence of numbers, so I evaluate this polynomial at, well, the first root of unity, that's or sort of the simplest one, which is just 1. We get this term, which just gives us the sum of all the coefficients. And the next term will be p omega 1n. The next term will be p omega 2n, etc., all the way up to, oh shit, I'm using here n, but it should be d, of course. Actually, that should be d plus 1. Yes, that should be d plus 1. My bad. Let's put it in here, d plus 1 to be consistent. D plus 1, d plus 1. And here we have d plus 1. Am I doing that correctly? Yes, I'm doing that correctly, I believe. So this gives us some new list of numbers, and this will be the Fourier transform of our original sequence of coefficients. So I thought that was kind of a cute observation that I hadn't seen before. Normally when we see Fourier transform, we just interpret it as, okay, we have a list of numbers, we just attach these complex numbers to them, these phases, and then we get out the right answer. But here it's sort of baked in by the fact that we already have these x to the power m terms in our polynomial. So if we just plug in the roots of unity, everything works out. One thing you might notice is that I'm both doing explaining things and sharing my thought process at the same time. Some of these things I would go faster through if I were to do them in my head, but or write them on a piece of paper. But it's also good to be very explicit, both for myself and for the audience, I guess. All right, so we have this nice connection now. Let's investigate this. Now, the first thing you should do when you have two different ways of thinking about a problem is trying to see how different things translate between pictures. Okay, what do I mean with that? Here we have a polynomial described by its list of coefficients, but also we have it expressed in terms of by evaluating the polynomial at roots of unity, we find a Fourier transform, and that also tells us something about our original polynomial. So let's take maybe something very simple. If I have a polynomial with these coefficients, meaning that just we just have a constant term, we can wonder, okay, well, how does then the Fourier transform look like? Well, we know from standard classes that the Fourier transform of a very sharply peaked distribution should be a uniform distribution when we take the Fourier transform. And that is sort of clear, right? Because if I evaluate a constant polynomial, it doesn't matter where I evaluate it, I will still get, I will always get the same value. I'll just get out 1. Okay, so that's another way of seeing this property that if I have a constant polynomial and I evaluate it at all roots of unity, I get constant value, which leads to a uniform distribution. So here I have the terms a sub m on the left side. And sort of on the Fourier side, I get this uniform distribution. Okay, that's not too surprising, but I think it's a cute observation at least. Okay, similarly, if we take the Fourier transform of a flat distribution, we should get a very peak distribution in the Fourier picture. Okay, so let's do that. How does this polynomial look like? Well, this is just a sum like this, right? And how does the sum look like? Well, this is just this term. But this is just a geometric series, or partial geometric series, which is of the following form. Let's see, I honestly keep forgetting, is it x to the d plus 1 or just d? I'm not too sure. I want to say it's d plus 1. Actually, let's double check that. How are we going to double check this? Well, let's check it in a trivial case. Let's plug in d is 1. And if d is 1, we just get out, let's see, that there's something wrong here. No, this is right. If d is 0, then we should get out 1. Am I saying that correctly? Is that right? Yes. Yeah, that works out. By now it's already quite late, so my brain is not that fast anymore. Just to be clear, if we plug in x is, d is 0, we get here x to the power 1. Well, that's nothing, divided by, which is just 1. And if I look at the sum, if this just goes up to d is 0, then I just have x to the 0, but that's just equal to 1. Let's do one further check. If d is 1, then I get 1 plus x should be equal to 1 minus x squared divided by 1 minus x. But we know that 1 minus x squared is, if we take, we know, of course, that 1 minus x times 1 plus x, if you expand it out, gives you exactly this term here, so that checks out. Right, just as a double check, as a sanity check, always good to do. Okay, let's see. So for this quotient list, right, this very flat distribution, we get out this geometric series, which is this polynomial here. And we now can plug in the different roots of unity. Okay, well, the nice thing is that if we plug in a d plus 1th root of unity in this expression, then the numerator will be 0. Because that's one of the defining properties of a root of unity, right? Because we have a root of unity, and raise it to the d plus 1th power. That should give us 1. That tells us the numerator is 0. But of course, we need to be careful. The denominator can also be 0 when x equals 1, right? We sort of get this trivial root of unity. Let's see. So let's assume that's not the case. Then we get out 0. So except for the first one, which we get out of mystery value. Well, I'll plug it in later. But for the rest, we'll get 0, etc. Now, for the first term, there's several ways to see what happens. If you plug in just 1 in the expression here, you just get d plus 1 terms. So you get a d plus 1 here, which is just a very sharply peaked distribution. I'm going to stop here because I'm getting some notifications. Might also just be a good place to stop as a first experiment.